All right, so we're taking a look at 3.4b, and as promised, we're looking at some word problems for linear programming. So we're starting out with an example of a farmer who has a set amount of land, 90 acres, available to plant two different types of seed, alfalfa and millet. We're looking at the cost for each type of seed. We're looking at labor costs. We're looking at expected income. We're looking at a budget for seed and labor. So we have a lot going on here, so let's try and dissect some of this. The first thing that we want to do is identify our variables, or assign our variables. I'm going to use variables that make sense in this situation. We're looking at planting two different types of seed. We've got the cost for the seed, we've got the labor cost for each seed, we've got expected income. So as I'm looking through all of these different pieces of information, they all lead back to alfalfa and millet as our two different variables. So I'm going to assign A for alfalfa and M for millet so that I don't try and confuse myself with what does X represent, what does Y represent, and have to keep going back and double checking. So now I'm going to start setting up my inequalities. So a farmer has 90 acres available for planting. So the amount of alfalfa that is planted plus the amount of millet that is planted has to be less than or equal to 90 acres. Second sentence, seed costs $6 per acre for alfalfa and $4 per acre for millet. Notice this is color coordinated. If we jump down to the next orange sentence, the farmer intends to spend no more than $480 for seed and $1,400 for labor, but labor is separate. So we're going to look at the seed. So $6 for alfalfa plus $4 for millet has to be less than or equal to no more than $480. That is our entire budget for seed. All right, our green sentence is labor costs. $10 per acre for alfalfa plus $20 per acre for millet, and we want to spend no more than $1,400 on labor. All right, the next piece of information that we're looking at is our expected income. We want an objective function to maximize profits. So that expected income is not part of our constraints, that is our objective function. So I'm going to say P equals 150A plus 110M. And that's the function we're going to try to maximize. We are not going to be graphing that. And a couple of other constraints that we didn't actually mention, but that makes sense, is that A has to be greater than or equal to 0, and M has to be greater than or equal to 0. So of course we're going to start with our X and Y axes as borders. I'm not even going to bother redrawing those. But I'm going to choose to put, since I did all of these with alfalfa first, I'm going to go ahead and put alfalfa on my x-axis. Alfalfa. And then the millet will be on my y-axis. Alright, so I'm going to find my intercepts. Obviously for my first inequality, A plus M is less than or equal to 90. 90 is going to be my intercept for each one. And I scaled my axes by 10. And these are all or equal to's, so that makes it nice, no dotted lines to think about. My next one, finding the intercepts for, this was the cost for seed. So 480 divided by 6 gives us an x-intercept of 80. And 480 divided by 4 gives us a y-intercept of 120. And the labor costs, 1400 divided by 10 gives us an x-intercept or an alfalfa intercept of 140. And my millet intercept would be 70. All right, so we need to take a look at where the feasible region is. Now, all of these were less than or equal to, which points towards the origin. So right here is going to be my shaded region. And again, in order to maximize the profit, I need to know where those vertices occur. So right here, of course 0, 0, but that's not going to maximize profit. here, here, or here. Now, more than likely, it's going to be a combination of alfalfa and millet that will maximize profit. So I would check those two vertices first, but then we still have to check our X and Y intercepts in order to see if maybe we just plant alfalfa, that will truly maximize our profits. So again, looking at my graph, I don't have a clear idea of where these intersect because my lines aren't perfectly straight. So we would go ahead and solve the system in order to see. I need to know where my red and my purple line intersect. So I'm going to go ahead and substitute 90 minus m for A. And remember, we're solving where they are equal, so we don't have to worry about that inequality when we're solving our system. So I'm solving this by substitution. Minus 6m plus 4m. So my m value would equal 30. So my alfalfa would be 60. So that is this point right here. Alfalfa was 60, millet was 30. So now we need to find this point where my green and my purple intersect. So I'm going to go ahead and use substitution again, that same 90 minus m for A. So solving this quickly, we've got minus 10 plus 20. So subtracting 900 and dividing by 10, we get an m value of 50. So alfalfa would be 40. So that's this ordered pair right here. And then in order to see which ordered pair maximizes our profit, that's where we're going to go ahead and use that objective function. So we've got our XY coordinates, our profit function, and we want a max. So we have 4 ordered pairs that we have to check. Right here, that would be 80, 0. And right here, that's 0, 70. So substituting each of these in, I'm not going to waste time writing it down. My first one gives me $11,500 profit. My second one would give me a profit of $12,300. My third one would give me a profit of $12,000. And my last one would give me a profit of $7,700. So my second one, again, you have to somehow make a note to me that you know planting 60 acres of alfalfa and 30 acres of millet will maximize profit. 60 acres alfalfa, oh, that should be it, and 30 acres of millet. And it makes sense that he would use his entire field. The last 2 ordered pairs, he's got 10 and 20 acres of his field that he's not planting. So of course that's not going to help maximize his profit.